We had learned about the concept of area moment of inertia. We had seen its physical significance, and we had also seen the general formula for finding the moment of inertia of any plane figure. Plus, we had seen a couple of examples of how we find the moment of inertia. Okay, we had seen the example of a general curve, which was, I think, a parabolic curve. We have seen the area moment of inertia of a circle. Plus, we have also seen the area moment of inertia of a rectangle. After that, we had also seen the use of the parallel axis term for finding the area moment of inertia about any axis which is parallel to the centroidal x-axis or centroidal y-axis. Okay, so here in this module, let's learn about the proof of parallel axis term. For studying this proof of the parallel axis term, I have taken a lamina of an arbitrary shape. Okay, you can see that this is a lamina of arbitrary shape whose area is equal to A. Okay, this area is equal to A. Now here I have shown two axes. One axis is shown with the green color. This is the centroidal x-axis. Okay, this axis is an x-axis, but it is passing through the centroid of the plane figure. Therefore, the centroid must lie somewhere here, and hence this is the centroidal x-axis. And another axis has been shown by this red color. Let me say that this is the x-axis, and about which I have to find the moment of inertia. Okay, I am interested in finding the moment of inertia about this axis, and you can see that this axis is parallel to centroidal x-axis. Okay, this axis is parallel to the centroidal x-axis. Oh, this is the centroidal axis. There are certain distances which need to be defined, but first of all, let me see that this is the differential element. Okay, this is a very small element whose area is equal to dA. And this differential element having an area of dA has been taken at the distance of, suppose, y dash from this centroidal x-axis. Okay, its distance from the centroidal x-axis is y dash, and there is another distance which needs to be defined, which is the distance between the centroidal x-axis and this x-axis about which I am interested in finding out the moment of inertia. Let's denote this distance by d. And there is another distance. It is the distance of the elemental area from the x-axis, okay, about which we have to find the moment of inertia, which is parallel to the centroidal x-axis. And from the figure, it is clear that this distance will be the summation of y dash and d. Okay. Now I'm interested in finding the moment of inertia about this x-axis, okay, shown with the red color. Therefore, I will first of all take an elemental area dA and find its moment of inertia about the x-axis. Okay, so from the basic definition, we know that moment of inertia of this small differential element about the x-axis will be equal to the distance, the square of the distance of the differential element from this axis, that is equal to y dash plus d. Okay, and we have to take it to square. Therefore, square of the summation of y dash and d, okay, and dA. So from this basic formula, we know that the moment of inertia of this differential element about this x-axis will be given by the square of the distance multiplied with this elemental area. Okay. Now, for finding the moment of inertia of this complete lamina about the x-axis, we can perform the integration. That will be given by integral of y dash plus d square dA. Okay. Now this is the moment of inertia of this complete lamina about the x-axis. Now let's break this. We can just evaluate this expression that will be equal to y dash square dA plus integral of d square into dA plus integral of 2y dash d into dA. Okay, so what I have done here is I have just evaluated this expression, okay, a plus b whole square, and I have then broken this integral into the three integrals. Okay, I have broken this integral into the three integrals. Now let's see one by one what does each integral represent. Okay, one by one, what does each integral represent? So see the first integral. The first integral is equal to y dash square dA. Okay, so from the basic definition, let's first see what is the distance of the, what does this distance y dash represent? This y dash represents the distance of the elemental area from the centroidal x-axis. Therefore, y dash square dA from the basic definition of the moment of inertia should be equal to area moment of inertia about centroidal x-axis. Okay, that is cx-axis. Okay, from the definition, it is clear that this integral, okay, y dash square dA gives us the moment of inertia of the plane figure about the centroidal x-axis. Now coming on to the second integral, that is equal to d square dA. Okay, I can take this d out of the integral as it is a constant, and I can perform the integral dA that will be equal to the complete area of this lamina. Okay, dA is the differential area. Okay, its integral will give us the total area of this lamina. Okay, hence I can write it as AD square. Okay, now let us focus our attention on this third integral, that is integral of 2y dash d dA. The integral here is 2y dash d dA. Okay, taking out the constants out of the integral 2d, we are left with y dash dA. Now, what does this represent? So first of all, I can draw the lamina again. This is the lamina, and suppose this is the centroidal x-axis, and I had taken a differential element dA. This is the differential element, and this was our centroidal x-axis. And since this is the centroidal x-axis, therefore the centroid of the lamina will be lying somewhere here. Okay, and we had defined this distance. This distance is equal to y dash. So now clearly see what does this integral represent, y dash dA. It represents the first moment of this area. Okay, this complete area, it is the first moment of the area or lamina, I can say. It is the first moment of this lamina about which axis? About centroidal x-axis. Okay, because this y dash is the distance of the differential element from the centroidal x-axis. Therefore, its integral, that is y dash dA, will represent the first moment of the area or lamina about the centroidal x-axis. Okay, now what is the first moment of the area about the centroidal x-axis? This term is always equal to 0. You can directly remember the statement that the first moment of the area or lamina about the centroidal x-axis or the centroidal y-axis. Okay, for our analysis currently I am taking the centroidal x-axis. Okay, but the result will be true for the centroidal y-axis as well. So this first moment of area is always equal to 0 about the centroidal x-axis, whether it is x or y-axis. Okay, so this will be equal to 0. Now how can I say that this is equal to 0? So see here, if I am if I am talking about Okay, if I'm talking about find the now if I tell you to find the y coordinate of the centroid of this lamina, okay, I ask students to find the y coordinate of the centroid of the lamina. Okay, obviously students will ask about which axis we have to find the y coordinate of the centroid. Okay, I tell them to find the y coordinate of the centroid about centroidal x-axis. Okay, that is this axis given here in the figure. I tell the students to find the y coordinate of this plane figure about the centroidal x-axis. Okay, so what will be the general formula? They will start by taking an element at a distance of suppose y dash from the centroidal x-axis. Okay, then the x coordinate, this y coordinate of the centroid, okay, y coordinate of the centroid of this element about the centroidal x-axis, they will write the formula that it is equal to y dash dA, integral of y dash dA divided by integral of dA. But look at the figure. I am asking you to find the y coordinate of the centroid about the centroidal x-axis. That is the distance above or below of the coordinate of the centroid above or below the x-axis, okay, the centroidal x-axis. Obviously, that coordinate will be equal to 0 because this centroid is lying on the centroidal x-axis, okay. Centroid is on the c-x-axis, therefore, its y coordinate will be 0, but with respect to which axis? With respect to this centroidal x-axis. Obviously, its y coordinate, suppose I am taking an example of any general axis, x dash x dash axis. I am asking you to find the coordinate of the centroid of this plane figure about this axis. Obviously, that will be given by this distance, okay, whatever the distance may be. But about the centroidal x-axis, the coordinate of the centroid is 0. That is the y coordinate is 0, okay. So let's rub this off. Therefore, from this equation, you can see that this y coordinate is 0, okay, y coordinate of the centroid, but about which axis? About cx axis, okay, about the cx axis. So from here, we can get that since integral of dA, okay, it has some area, it can't be 0. Therefore, this term is 0. Y dash dA is equal to 0, okay. And what does this give us? This gives us the first moment of the area or the lamina about this particular x-axis, which is the centroidal x-axis, and this result will always be 0, okay. It is an important result with respect to the objectives, okay. The first moment of the area about centroidal axis is 0, whether it is x-axis or y-axis, okay. So we can see that we had broken this integral into the three integrals, okay. This first integral, we saw that it is equal to ICX, this is equal to AD square, and this integral now evaluates to 0. Hence, we can write the final result that moment of inertia about any axis which is parallel to the centroidal x-axis will be equal to the area moment of inertia about the centroidal x-axis plus the product of area and the square of the distance between these two axes. Okay. So this is the mathematical representation of the parallel axis theorem for an area. And we also expect the students to find the proof, okay, to derive the proof, to prove that the moment, this what we call as this area, this mass moment of inertia, okay, parallel axis term for the mass moment of inertia as well. Only the terms of area will get replaced by mass, the rest of the procedure will be same, okay. So this derivation is quite important with respect to the examination, okay, offline examination. So whether it is asked about the area or it is asked about the mass, the procedure will remain same, only the area and the mass terms will get interchanged, okay. So this is parallel axis term for an area, okay. So we have also seen the use of this formula, okay, of this term, and in the further questions we can again see the use of this term. Let us focus now our attention to the moment of inertia of the composite areas. the moment of inertia of the composite areas. Okay, and we have studied the moment of inertia, mass moment of inertia of the composite bodies as well. Okay, there we had seen that a body can be broken into various elements whose moment of inertia is known. Okay, some simple shapes. Similarly, in this analysis, we can do is that the given area can be broken into various simple shapes whose moment of inertia are known to us. That means we can break the composite area into various small shapes, okay, various shapes whose moment of inertia are known to us. Suppose we can break uh, an area into the circle, we can break it into semicircle, we can break into rectangle, triangle, square, okay, जिनका हमें moment of inertia पता होता है. So the area can be broken into simple shapes whose moment of inertia are known. The total moment of inertia of the composite area about a given axis will be equal to summation of moments of inertia of the various components or shapes, okay, various components, or we can say the shapes, the components in which the original body was broken into components or shapes about that axis. Okay, so moment of inertia of a composite body will be equal to the summation of the moment of inertia of individual shapes or elements. Okay, so we had seen this result in the mass moment of inertia as well. We had seen a couple of questions there as well. So same applies to the area moment of inertia. Okay, let's discuss the moment of inertia of a composite body. Okay, an example of moment of inertia of the composite figure. Okay, you can see in the figure there is an L section given. Okay, there is an L section given. So this L section can be broken into two rectangles. Okay, you can clearly see that it is a composite of two rectangles. Okay, so let's write the dimensions first. This is equal to 2 meters. This distance is equal to 6 meters, and this distance is equal to 2 meters, and this dimension is again equal to 6 meters. Okay, so what can we do here is we can break this figure into two rectangles. Okay, so the first rectangle, let me take that. This is the first rectangle. Okay, and then this second will be the complete rectangle. Okay, so the dimensions of the first rectangle will be, okay, this is the first rectangle, its dimensions will be 4 meters and 2 meters. You can see that this 6 minus 2, this length will be 4 and this width is 2 meters. Similarly, this length will be equal to 2 meters. Therefore, the total length of the second rectangle will be equal to 8 meters and its width is equal to 2 meters. Okay, this is the breakdown of this figure into two elemental shapes whose moment of inertia are known to us, and these are the two rectangles. Okay, so let us find the moment of inertia about centroidal x and y axes. Obviously, moment of inertia is always defined with respect to certain axes, about which axes we are interested here. As per the question, we are interested in finding the moment of inertia about the centroidal x and centroidal y axes. Okay, so therefore, to see which is the centroidal x axis and centroidal y axis, we must know the location of the centroid. Okay, obviously, once we know the location of the centroid, we can figure out the centroidal x-axis and centroidal y-axis. Okay, so first here, the basic thing by which we have to start is finding the centroid. So x coordinate of the centroid will be given by a1 x1 plus a2 x2 divided by a1 and a summation of a1 and a2. Okay, so this formula, we have already done the problems on this formula. Okay, it's just the review. So x bar will be equal to a1. Okay, the area of this first rectangle is equal to 4 into 2, that will be equal to 6. 4 into 2, sorry, it will be equal to 8. And x means the distance of the x coordinate. Okay, x1 means the coordinate, x coordinate of the first rectangle. Okay, x coordinate of the centroid of the first rectangle. So see here, before finding the centroid, I must again define the reference x-axis. This is the reference x-axis and this is the reference y-axis. So this is the first rectangle. It will have some its own centroid here. Let me say that this is equal to C1. Okay, the C1 is the centroid of this first rectangle, and its x coordinate is equal to, this distance will be equal to x1. Okay, this distance is equal to x1. That is, it is the x coordinate of the centroid of the first rectangle. And you can see that this distance is equal to 2. Therefore, its centroid will lie at the half. That will be equal to 2 by 2. That will be equal to 1 plus a2. Okay, the area of the second rectangle is equal to 8 multiplied by 2. That will be equal to 16. And you can see that this area will again have its own centroid, which is denoted by C2. And this x2 is the x coordinate. It is the x coordinate of the centroid of the second rectangle. Okay, this is the x coordinate of the centroid of the second rectangle. Okay, you can see that this complete distance is equal to 8. Its centroid will be lying at half. Therefore, 8 by 2 will be equal to 4. The areas will be 8 plus 16. So we can see that this x bar will be equal to, it will be equal to, this is 8 plus 64. This will be equal to 24. And this will be equal to 72 by 24. So this x bar will be equal to 3 meters. That is, the centroid of this complete figure will lie at a distance of 3 meters from this reference axis. Okay, this reference y axis. Now similarly, we can find the y coordinate of the centroid of this figure. Let's introduce the figure again. Now I'm interested in finding the y coordinate. I had broken this into two rectangles. This is the centroid of the first rectangle and this is the centroid of the second rectangle. Okay, these distances were 2 meters. This was again 2, this was 6, this was 6, and this was 2. I had initially found out the x coordinate of the centroid. Now I am finding the y coordinate of the centroid, and as per the general formula, it is equal to a1 y1 plus a2 y2 divided by a1 summation of a1 and a2. Now these y1 and y2 are the centroid coordinates of the centroid of the first rectangle and the second rectangle respectively. So this will be our reference x-axis, this will be our reference y-axis, about which we are measuring these coordinates. Okay, So we can see that y1 will be in this figure, it will be equal to this distance. This distance is equal to y1 and this distance is equal to y2. So let's see what is y1. Y1 will be equal to, you can see that this distance is equal to 4. Okay, this distance is equal to 4. Therefore, the centroid of the first rectangle, see here, this is the first rectangle. Its centroid will lie at a distance of 2 meters. Okay, this will be the centroid. Okay, since the length of this first rectangle is equal to 4, therefore its centroid will be at half. But what will be the y1 distance? It will be this 2 plus this 2, because I am measuring this coordinate from the reference x-axis. Okay, y1 is the distance from the reference reference x-axis. Therefore, this is the complete distance, which is equal to 2 plus this 2. Therefore, y1 will be equal to 4. Y2 is easier to locate. It is at a distance of, since this height is equal to 2, its centroid will be at a height of half, that is equal to 1. So we can figure it out here that area is equal to, again, first rectangle is equal to 4 into 2, that will be 8. This y1 is equal to 4 plus the area of the second rectangle is equal to, this is again 2, 8 into 2, that will be equal to 16. This distance is equal to 1. And the summation of the areas is 8 plus 16. Okay, this will be 32 plus 16, that will be equal to 48 divided by 24. And this distance now, y bar will be equal to 2 meters. So we have obtained the coordinates of the centroid of the complete figure. Okay, C now represents the centroid of the complete figure, that is equal to 3, 2. X coordinate is 3 and y coordinate is equal to 2. Okay, so now let's locate the centroid of this figure. We have found the coordinates and now we can show its location. The coordinate was 3, 2. That is y coordinate should be equal to what? Y coordinate should be equal to 2. This distance was 2. Therefore, the centroid will lie on this line, somewhere on this line, okay, at a height of 2 meters. And how much in front of the y-axis will it lie? This is the y. This is x-axis, okay. Kitna in front lie karega? That will be given by x coordinate, which was equal to 3. So this distance was 2. Therefore, 3 should be somewhere here. This should be the location of our centroid of the complete figure. Okay, this will give us the location of the centroid of the complete figure. Okay, so C1 and C2 were the centroids of the individual rectangles, but the C is the location of the centroid of the complete figure. Okay, now see here, once we have found out the centroid, we are interested in finding the moment of inertia about the centroidal x-axis and centroidal y-axis. Now currently my focus will be on the moment of inertia about the centroidal x-axis. Now see here, this is the centroidal x-axis because it is parallel to the reference x-axis and it is passing through the centroid. Therefore, I say that this is the centroidal x-axis. Okay, this will be our centroidal x-axis, and similarly, this will be our centroidal y-axis, which we can show later on. Okay. Now, to find the moment of inertia about the centroidal x-axis of the complete figure, since I have broken it into two rectangles, 1 and 2, okay, so I will first of all find the moment of inertia of this first rectangle about the centroidal x-axis, and then I will find the moment of inertia of the second rectangle about the centroidal x-axis, and I will make the summation of these two to find the moment of inertia of the complete figure about the centroidal x-axis. Okay, so let's calculate the moment of inertia of the first rectangle about the centroidal x-axis. Okay, so I don't directly know the result of the moment of inertia of the first rectangle about this centroidal x-axis of the complete figure, but what I know is the moment of inertia of this rectangle about its own centroidal x-axis. This is its centroid. this is the centroidal x-axis, but of the first rectangle. Okay, remember it is of the first rectangle whose width is equal to this length is equal to 4 meters. Okay, so since I know the moment of inertia of this first rectangle about its own centroidal x-axis, I can make the use of parallel axis term to find the moment of inertia of this first rectangle about the centroidal x-axis of the complete figure. Okay, hope it is clear. So I1 will be equal to moment of inertia of the first rectangle about this x-axis. Okay, about this x-axis. Okay, so it will be equal to moment of inertia about its own centroidal x-axis. Okay, so this Ix is what moment of inertia about the centroidal x-axis of the complete figure. That should be equal to moment of inertia of the centroidal x-axis about its own centroid. Okay, C1x is the its own centroidal x-axis. Plus, by the use of parallel axis term, I'm using the parallel axis term for the first rectangle. Therefore, I will write the area of the first rectangle multiplied by the square of the distance between these two axes. Okay, so this is the distance between these two axes, and it can be seen from the figure that it will be equal to 2. This distance will be equal to 2 because this is complete 6. This distance is equal to 2. Rest of the distance will be 4. 4 ka half jo ho jayega, that will be 2. Okay. So moment of inertia of the first rectangle about its own centroidal x-axis, we know its formula. It is equal to one dimension. Okay, remember 6 is not the complete dimension. This rectangle is only up to this. That is 4 into 4 into 2 cube by 12. Okay, sorry, this will be equal to 2 into 4 cube by 12. Okay, if this is b, if this is d, then about its x-axis, about the centroidal x-axis, the moment of inertia will be bd cube by 12. So b is 2, depth is equal to 4, therefore 2 into 4 cube by 12, plus the area of the first rectangle is equal to 2 into 4, and the distance between these two axes about which I'm applying the parallel axis term is equal to 2, therefore square of 2. Okay, so this after solving this, it will be equal to 42.66 meter to the power 4. Okay, this is the moment of inertia of the first rectangle. Okay, about the centroidal x-axis of the complete L section. Okay, about the complete L section. I would also recommend the students to check the calculations themselves as well. There might be some error, so they can check themselves as well. Now we are going to find out the moment of inertia of the second rectangle about the CX axis. Okay, second rectangle about the CX axis. I can also make a correction here. We can write like this: centroidal x-axis of the complete figure. Centroidal x-axis this is the moment of inertia of the second rectangle about the CX axis. This means the moment of inertia of the first rectangle about the CX axis. Okay, that should be equal to I C2x, its own centroidal x-axis. Okay, its centroid will be somewhere here, and its own centroidal x-axis will be this axis. And this is the distance between the two axes, and you can see that this will be equal to 1. Okay, so IC2x means this is the moment of inertia of the second rectangle about its own centroidal x-axis, but we are interested in finding the moment of inertia about this CX axis. Therefore, I need to use the parallel axis term. Now I am taking this parallel axis term for the second area. Therefore, A2 multiplied by square of the distance between these two axes. Okay, so this will be equal to, now moment of inertia of the second rectangle about its own centroidal x-axis, that will be equal to b d cube by 12. Okay, this b here is complete today, this time it is equal to 8. Okay, this is equal to 8, therefore it will be 8 into the depth is equal to 2, d is equal to 2, therefore 2 cube divided by 12. This we know from the basic formula. The area will be equal to 8 into 2, the square of the distance between them, that is 1 square. Okay, if we evaluate this, this should be equal to 8 into 2 cube by 12 plus 8 into 2, that should be equal to 21.33 meter to the power 4. Okay, so this is the centroidal, this is the moment of inertia of the second rectangle. Now we can find the moment of inertia of the complete figure. Okay, about which axis? About the centroidal x-axis, the complete moment of inertia about the centroidal x-axis, that will be given by moment of inertia about the centroidal x-axis of the first rectangle and the moment of inertia about centroidal x-axis of the second rectangle. Okay, the cx denotes the centroidal x-axis of the complete figure. Okay, so we can make their summation, that will be equal to 42.66 plus 21.33. Okay, so this will be near about 64 meter is power 4. Okay, so we have found out the moment of inertia about the centroidal x-axis. Now let's go for the calculation of the this moment of inertia about the centroidal y-axis. Again, introducing this figure here. The location of the centroid was here. Therefore, now this will become our axis about which we have to find out the moment of inertia. Again, this figure can be broken into two rectangles. This is the first rectangle. This is the complete second rectangle. First rectangle will have a centroid here, and we can find the moment of inertia about its own centroidal y-axis. Okay, this is the centroidal y-axis of the first figure. Okay, for second, the centroid will be here. We can also find the moment of inertia of the second rectangle about its own centroidal axis, and then we can use the parallax thumb to get the moment of inertia about the centroidal y-axis of the complete figure. Okay, so let's take first rectangle, moment of inertia of the first rectangle about the centroidal y-axis. Okay, moment of inertia of the first rectangle about this centroidal y-axis, but it is of the first rectangle, that will be equal to moment of inertia of the first rectangle about its own centroidal axis. Okay, about its own centroidal axis, just like we did in the previous slide, plus the area into area of the first rectangle and the square of the distance between these two axes. Okay, so IC1 will give the moment of inertia of the first rectangle about its own centroidal axis, that will be equal to, this will be equal to db cube by 12. Okay, now depth here is 4 meters into b cube, this distance is equal to 2, 4 into 2 cube by 12, plus area will be equal to 4 into 2, the distance between these two axes. Now see here the distance between these two axes. We have found out the x coordinate of the centroid. The x coordinate of the centroid was equal to 3. Okay, that is, this distance is equal to 3 meters. The x coordinate of the centroid is equal to 3 meters. That is, this is 3 comma 2. Okay, this distance is equal to 3 meters. Now see here the centroid, this distance will be 1, this distance is also 1. Okay, this distance is also 1. I am interested in finding this distance. Okay, that will be equal to, this complete distance is 3, minus this one from here. Okay, so this distance will be equal to 3 minus 1, that will be equal to 2. Okay, so the distance between these two axes is equal to 2, therefore 2 square. Okay, after solving this we can see that 4 into 2 cube by 12 plus 4 into 2 into 2 square, this comes out to be 34.67 meter to the power 4. Okay, it comes out to be this much. Similarly, we can find out the moment of inertia of the second rectangle about this axis. Okay, so moment of inertia of the second rectangle about centroidal y-axis is equal to, first of all we will find the moment of inertia about its own centroidal x-axis, centroidal y-axis, that is moment of inertia of the second rectangle about its own centroidal y-axis plus area of the second rectangle multiplied the distance between these two axes. Now for that, this distance need is to be found out. Okay, so moment of inertia of the second rectangle about its own centroidal x-axis will be equal to dB cube by 12. So d is equal to, this is the distance 2 into p cube, this p is equal to 8 plus area is equal to 8 into 2. Now this distance needs to be found out. Okay, we can see that this complete distance is equal to, okay, since this is 8, therefore centroid will lie at 4. Now this distance is equal to 3. Okay, इसकी जो distance है from the reference y axis, that is equal to 4, and this distance is equal to 3. Therefore this distance will be equal to 4 minus 3, that will be equal to 1 meter. Okay, so the distance between these two axes is equal to 1 meter and it's squared. So if we evaluate this result, 2 into 8 cube by 12 plus 16, that should be equal to 101.3 meter to the power 4. Okay, meter to the power 4. So now for finding the total moment of inertia about the centroidal y-axis, we can make the summation of these two individual moment of inertia, that is 34.67 plus 101.3. So this should be near about 136. Okay, it will be near about 136 meter to the power 4. Now let's see one more question on the composite moment of inertia. Okay, so in this question we have to find the moment of inertia about this x-axis. Okay, moment of inertia about x-axis, and that too of the shaded figure only. Okay, so this shaded figure is actually, you can see that a circle has been cut out from this rectangle. Okay, this would have been a complete rectangle and a circle is cut out at the center of the rectangle whose radius is equal to 25 mm. The remaining figure is this shaded figure. Okay, so this is a cut out portion. Okay, some area has been cut out from a particular area, then in those cases the moment of inertia will be equal to the difference. Okay, difference between the moment of inertia. So in this case you can see that the original figure was what, a rectangle. So in this case the moment of inertia will be equal to the moment of inertia of the rectangle, complete rectangle. Okay, first of all we will assume that this is a complete rectangle. You can see that initially this would have been a complete rectangle. Okay, this is the complete rectangle. So the moment of inertia about this x-axis will be equal to moment of inertia of this complete rectangle about the x-axis at minus, okay, you can see that this circle has been cut out from it, the moment of inertia of this circle from with reference to this, okay, x-axis, with respect to the x-axis. So the moment of inertia will be equal to moment of inertia of the rectangle minus moment of inertia of the circle. Okay, so individually we will compute the moment of inertia of these components about the x-axis. Okay, so if we take an example of this complete rectangle, okay, the dimensions are 100 and 150. we have to find the moment of inertia about this x-axis, but we don't directly know the result. Therefore, we can use the parallel axis term because we know the moment of inertia of the rectangle about its centroidal x-axis. Therefore, I rectangle about the centroidal x-axis, about this x-axis, okay, complete x-axis, this x-axis, which is given here in the figure, that will be equal to moment of inertia of this rectangle about its own centroidal x-axis. Okay, this is its own centroidal x-axis, plus we have to make the use of parallel axis term, that is area of the rectangle multiplied by the square of the distance between these two axes. Okay, this is the x-axis, this is the centroidal x-axis, and this is the axis about which we have to find the moment of inertia, and it is given here this distance will be equal to 75 mm. Okay, it is obvious that this is 150, its centroid will lie at 75 mm. The distance between these two axes will be equal to 75 mm. So by the formula, we know I rectangle about its own centroidal x-axis, that is BD cube by 12. Now here B is equal to 100. Okay, it is equal to 100, and D is equal to, sorry, B is equal to, yes, B is equal to 100 and D is equal to 150. Therefore 150 cube divided by 12. Okay, and we have to add what? We have to add, I can rub this off. We have to add what? The area times area of the rectangle and square of the distance between the two axes. The area of the rectangle will be equal to 100 into 150. The square of the distance between these two axes is equal to 75. Okay, so we can see that the moment of inertia of the rectangle about the x-axis will be given by, it should be equal to, this result will evaluate to 112.5 into 10 to the power 6 mm4. Okay, this will be the result after the simplification of this, after the simplification. Okay, so what we have computed here, we have computed the moment of inertia of this complete rectangle about this x-axis. Now we have to subtract the moment of inertia of this circle about the x-axis. Therefore, the moment of inertia about x-axis I circle about x-axis will be equal to moment of inertia of this circle about its own centroidal x-axis plus area of this circle multiplied by the square of the distance between those two axes. Okay, so from figure you can see that the moment of inertia of the circle, okay, see here this circle, the center of the circle also coincides with what? It also coincides with this, what we call as the center of the rectangle. Okay, the moment of inertia of the circle, and you also know that the formula for moment of inertia of the circle about the centroidal axis will be equal to, okay, this is passing through the diameter. Okay, this axis passes through the diameter as well. It will be equal to pi d to the power 464. Okay, and if we have to write the same result in terms of the radius here, okay, in terms of the radius, it will be equal to pi r to the power 4 divided by 4. Okay, either in terms of the diameter you can use this formula, in terms of the what we call as the radius we will use this formula. Okay, so here we can write that moment of inertia of the circle about its own central x-axis will be equal to pi r to the power 4 divided by 4. Okay, this is its moment of inertia about its own central axis, but we are interested in the in this x-axis. Therefore we have to use the parallel axis term, that is equal to, that is we have to add to it the area of the circle and the square of the distance between these two axes. Okay, area of the circle, that will be equal to pi r square, the distance between these two axes is d, and d is equal to here 75. We can put the values here. Pi into the radius of the circle is 25. Okay, This will be equal to pi. The radius is equal to 25. The square of the distance between them, that is the distance is 75. Okay, so if we solve this expression, okay, if we calculate it, it will be equal to it will be equal to 11.4 into 10 to the power 6 mm4. Okay, so these were the individual moment of inertia of these complete rectangle and the circle about the x-axis. Therefore, net moment of inertia will be equal to I rectangle minus I circle. That should be equal to, the previous result was 112.5 minus 11.4. Okay, 10 to the power 6 can be taken as common. This is 10 to the power 6 mm to the power 4, and this will be equal to 101 into 10 to the power 6 mm4. Okay, actually it will be 101.1. We can take it as to be 101 into 10 to the power 6 mm to the power 4. Okay, so this is the way how can we can deal with the moment of inertia of the composite figures. Okay, the simple concept is that break the figure into this what we call as the simple shapes. Okay, the composite area can be broken into various simple shapes, but their moment of inertia should be known. Okay, we have seen we are breaking them into a rectangle whose moment of inertia is known. We are breaking them into a circle whose again the moment of inertia is known. Okay, we can further break down them into squares or triangles whose moment of inertia is known. Okay, and then later on we will add them or subtract them as per the requirement of the question. In the L section, we had to add up those two moment of inertia because that combined figure would have been given by the addition of those two rectangles, and here the figure which was the shaded figure would have been given by the subtraction, okay, of the circle from the rectangle. Okay, hope this is clear. I expect the students to solve further questions from the book.